So, let me begin my presentation. My name is Daisuke Endo from the Public Works Research Institute in Japan. Today, I'd like to introduce a new approach to improve the path tracking accuracy of hydraulic excavators by embedding an angular velocity controller directly inside the machine. This work is part of a joint research project with Hitachi Construction Machinery. In Japan, due to declining birth rate and aging population, there's a growing need to automate construction machinery. Our public research institute have been working on the automation of hydraulic excavators, which are one of the most common construction machines. On the left, you see manual operation by a not-so-skilled operator. On the right is the same task performed by an automated system. As you can see, the automated motion is slower and less precise. It's clearly inferior both accuracy and efficiency. One major reason is hydraulic excavators were originally designed for human-operated lever control, which is not so easy to be integrated with automation systems. So, to overcome these issues, we focused on two key objectives in this research. First, we aim to improve the accuracy of bucket edge path tracking during excavation tasks. Second, we want to make the automation of hydraulic excavators more accessible to third-party developers. By allowing external control without complex system integration, these two goals support both performance and usability, which are essential for advancing practical motion in the field. Why is it hard to control an excavator from outside using lever commands? One reason is the complexity of the hydraulic system. The left diagram shows how levers in the cab control valves, which move actuators like cylinders and motors. In general, the number of pumps is fewer than actuators. When you move a lever, there's a time delay before the machine starts moving. This is called dead time. In addition, the response changes depending on how many joints are moving together. This is so-called coupling effects. Dead bands also are added to help human operators, but they can reduce precision in case controlled by external system. And during digging, the load from the soil changes a lot and is hard to predict. These factors make external control based on levers difficult and inaccurate. To address these issues, we propose embedding a joint velocity controller into the excavator. We added pressure sensors and the velocity control unit to the conventional vehicle with 2D machine controls. The unit connects to external systems, allowing direct joint velocity commands and feedback. With this, external control should become simpler and more precise. This is our key idea, which is inspired by general industrial robots. Next, I'll explain the difference between the conventional control architecture and the system we developed in this study. In both cases, shown here in the center, we used a 2D machine control-enabled excavator. As external upper system, the motion control unit sends commands to the machine in both architectures. The key difference lies in the intermediate control layer. In the conventional system, the motion control unit outputs lever commands, which are converted into target pipe pressures and sent to the solenoid valve controller. On the other hand, in our proposed system, the motion control unit outputs target angular velocities for each joint. These are received by embedded velocity controller, which calculates the appropriate pipe pressures using an internal velocity control algorithm. This velocity-based control interface simplifies the communication from the external system and enables more accurate and responsive motion. I'll explain details about this joint velocity controller in the next slide. This diagram shows the overall structure of the joint velocity controller we developed. The controller consists of three main steps, A, B, and C. Due to time constraints, I'll skip the details of step A and C. In short, step A converts joint angular velocities into cylinder speeds based on link kinematics. And step C calculates the required part pressure to achieve the target hydraulic flow using an orifice flow equation. The most important part is step B, which handles flow rate adjustment based on pump capacity and actuator demands. I will explain this step in more detail on the next slide. This slide explains step B of our control logic, how we calculate and distribute the available pump flow rate. The key idea is to maintain the ratio of angular velocity commands given to each joint, even when the total flow demand exceeds the pump's capacity. Let me break this down into two cases. First, when the total required flow to realize all target joint velocities is within the pump capacity. In this case, it's straightforward. We calculate the flow rate needed for each actuator Q in A and Q in B and apply them directly. The second case is when the total flow demand exceeds the pump's maximum output. For example, suppose the pump can deliver 100 units of flow, but the commands require 60 units for cylinder A and 90 for B. That totals 150. Since the pump cannot meet this demand, we scale both flows down while maintaining the original command ratio. In this case, multiply both by 100 over 150. Of course, this means the actual joint velocities don't match the original command. However, the path of the bucket edge, which the motion controller ultimately aims to follow, will still be preserved. This is the essence of our joint velocity control logic. To validate our method, we compared it with the conventional system using a Hitachi X200 excavator shown on the left. The test motion involved 4 point-to-point commands as shown on the top right figure. Step 2 moves only the arm. Step 3 moves the arm and bucket, and Step 4 moves boom and bucket simultaneously. We analyze the joint response and path tracking to evaluate performance of each system. These graphics show the actuator angular response for the boom, arm, and bucket joints. In all graphics, the horizontal axis represents time and the vertical axis shows joint angles. Dashed lines are targets, solid lines are actual motion. Left graph is the results from the conventional control system, and the right is those from the proposal system. In left side, you can see that the arm joint fails to reach its target during the excavating motion with remaining steady-state error. Furthermore, when both the arm and bucket were commanded to move simultaneously, the arm started moving fast, and after about 3 seconds the bucket began to respond, causing a nonlinear interaction that also distributed the arm's motion. In contrast with the proposal system, we see that the steady-state errors are significantly reduced. Both the arm and bucket start moving almost simultaneously during excavating, and the responses are smoother and more linear. These results in faster and more coordinated motion. Next, we showed the analysis results of the bucket edge path. The left graph illustrates the path of the bucket edge as seen from the right side of the excavator. The horizontal axis indicates the forward position, and the vertical axis shows the height. Red shaded mark the bucket chip orientation as the transition points between motion phases. As you can see, the proposed method achieves a path much closer to the target trajectory compared to the conventional method. We also calculated the root mean squared error between the actual and target paths. As a result, the proposal system reduced the error by approximately 59% compared to the conventional systems. Finally, I summarize this research presentation in this slide. The proposed control system significantly improved tracking accuracy and motion stability, make external automation system for excavators more precise and developer-friendly. That concludes my presentation for today. Thank you all for your attention.